Thank you, Kenny. Thanks, everybody. This is a really exciting thing to be a part of. I can't wait to see all the talks. I'm here to get people acquainted with the basics who might not otherwise be. So I'm just going to be covering the basics. So just to get an idea, like, who knows what a Merkle tree is? Or sorry, who doesn't? So I know who I'm talking to. You know, like, yeah, this is for you. Okay, maybe it's one person. Maybe there's some shy people. I'm going to try to go kind of swiftly. I'm going to try to do this as lovingly, smoothly as possible. And hopefully you'll come away with a better understanding of some of the fundamental pieces that this whole thing's made out of. Let me clip this on. Never mind. All right, so the first thing I'm going to give you is hashes, okay? We might as well call tonight Hash Fest because everything we're doing is like built on these cryptographic hashes. What? Hash bash? Yeah, if we do this again next year, we should call it hash bash. A hash is just it's a function. You give it some data, and it gives you out some random data of a consistent length. So you can see here I've got hello Seattle, and then hello Seattle with an exclamation mark, and then they give you two totally different numbers, right? So you can see that a small difference gives you a totally different output. It always gives you the same length output. And it should be very unlikely that two inputs ever give you the same output. So that's like a kind of interesting thing. And what's cool about that is once you have a hash of a file, you can pretty easily, you could pass that to someone. You could say, hey, this is my social security number's hash or something. And then you could prove if you ever had it, right? So hashes let you do some cool things regarding proving that you have some information that somebody else hashed, okay? Now, those get combined. When you take a hash of a couple other things, you can do something cool called a Merkle tree, right? So let's say we've got two different files. We could hash them into a hash, and then we could bundle that with another hash, and now we've got a hash of that. And that data structure has some interesting properties. For example, so this is one Merkle tree here. If we change one file here, and I think this metaphor is pretty cool. I haven't seen anyone do the color mixing, right? Color mixing is a pretty good metaphor for it, because you get out something that you could only get from the inputs, but you can't easily figure out what got you to that, right? Okay, so let's say we change one of these input colors, right? We change one file, and you can see that changes what that first color gets mixed into, which changes the resulting one. So if you just have the root hash, if somebody says, oh, here's my Merkle tree, here's the root hash, you can know, oh, okay, so I can prove if I ever have their whole hard drive. But then if they say, here's my updated thing, you can know something changed. And if they give you basically just up that branch, then you could actually have all the changes. And you could prove that the only things that changed were those things, right? Let's say you had all of these, and then you get that one new file. You can just go up there. You're like, okay, let me hash that. Yeah, it does create that. I can hash that. And you get the new result. And that's called a Merkle proof. Okay, so what it lets you do is it's a very cheap way to validate that a small piece of data is in a big data set. And this is really valuable when you're in a distributed network. We're like sharing some kind of database together, and I want to give you something that you can trust. So I want to give you as little as possible to like establish that trust, right? And that's kind of what a root hash is good for. There was a recent announcement like Apple's going to use their new file system is going to be based on Merkle proofs because they'll be able to tell as soon as a single file is corrupted, right? It's like if you can't prove the root hash, then you know a file's wrong, and then you can just go through, figure out exactly which one. So it's a really useful data structure. What else can we do with that? Oh, well, if you're a software developer, you're familiar with Git, and Git is just using these same Merkle trees. You may have not noticed you were using Merkle trees, but basically you've got all the files in your project, and when you change one, Git just saves that one and then gives you a new commit, and then you've got that commit hash, and then you can always check out a hash, and you can check out a hash at a different point in history, and it gives you these really cool properties. And you'll always hear programmers say, like, I just wish more people could have Git. I wish lawyers had Git. We could just have like version control the legal system, because you could see the one-line difference. Here's what I want. It's just that much different, but it's got a different root, and so you can prove that I'm only changing one line. Anyway, so Git's great. Git's very valuable, but that's not all you can do with Merkle trees. Okay, blockchains are another thing that use this data structure, where you're taking a file, you're taking a hash of it. And then you maybe just want to add another file to it. So you just now take the hash of that new file with your previous root, you get a new root. And so now what you can do is you can prove that this file came after that. Okay, and so now you've got this like kind of causality, and so you can always just kind of add something in, and then you get a new root. So as long as you've got a good way of getting that root, you have a good way of establishing trust all the way down. You can prove the entire order of history on this data structure. So this could be a hard drive, this could be a shared, to-do list at home, whatever that is. Right? The point is you add some data, you hash it together, and you keep moving forward, and you get this ordinality. To be fair, that's kind of only one half of what people call blockchains. Okay, that's like the block part. But I'll get to the consensus layer in a second, which is a fun thing. So Bitcoin is basically just that as a data structure, right? We take a list of transactions and we hash them with the original root. And what's cool about this is now we always know that these transactions happened in a certain order. And that's why Bitcoin, they say, solves the double spend problem. The problem that I could like tell two people that I'm giving them the same $50 and then them both saying, oh, I guess I got paid. We have to have a single source of truth to establish a kind of shared money system. And so that's kind of what Bitcoin established. They say, you're saying, okay, if we have blocks of transactions at a time, we know for certain these happened in that order. Okay, I'm gonna try to summarize this quickly. So when you've got this data structure with a lot of people, the hardest part is establishing what is that root hash that I'm gonna trust. I could just email it to you and you could just trust me, but that doesn't sound like very decentralized. I could just get corrupt. So how do we come up with a method of who gets to add the next block, who gets to add the next series of transactions to this ever-growing database? And what Bitcoin proposed is to have a consensus protocol. We've got a whole bunch of people that are basically racing to get to be the one who adds the next block to the blockchain. So Bitcoin does that with proof of work. So it's basically a really hard computer problem. I'm going to tell you, I'm not going to really talk about nonce because I'm trying to keep this quick. We have some amazing talks. But basically, computers racing it's just a one CPU, one vote. And they're just trying to get the privilege of adding that next block, which gets to decide the order of all the transactions, which is a powerful thing. So part of the point of these distributed systems is preventing any one source of power from getting to decide the final order, because that would just be too much power. The miners, of course, get an incentive to do this. Every time a miner successfully makes a correct block, they get some bitcoins, or in Ether they get some Ether rewards. Okay, so what's Ether? Ether's the same thing, but instead of a list of transactions at a time, we're taking a whole computer's state. So it's this whole virtual computer space, and then in one of these blocks is a series of transactions. They're like computer operations, like you sent an email, or you sent some money from one person to another, or you voted, or you finished a crowd sale. All these things are things a computer might do, and so all of those things would be state changes in a block. Then we get a hash, and then we start again, and it's this continuous process. So Ethereum's basically a virtual machine on a blockchain. A single block has a lot of things. It's got a timestamp, a hash, the hash of its parent. The important thing, though, is the list of transactions. So a transaction, each interaction you have with the blockchain, it's from you. You cryptographically sign it. You're the only person who can control your account. And then you can interact with these little programs that live on the blockchain called smart contracts. And every time you interact with the blockchain, also, you have to spend a little bit of Ether to incentivize the miners on it. And it prevents you from just spamming the network and bringing the whole thing down. Ideally, making the computer do things is priced in such a way that they don't want to harass it. So here's just some cool visualizations made by Kumavis over here. So here we've got the virtual machine state. Here on the edges, we've got user accounts. And here's some like contracts inside Ethereumville, okay? So you can, of course, send some Ether from one person to another. You could also send some Ether or call a method on a contract inside the machine. The contracts can also have side effects. So you could call, for example, you could have a bank account thing where you turn up your kid's spending limit, and then maybe their allowance, and then it sends to them, for example. Or there could be complex chain reactions. Maybe you change your voting preferences, and your legislation gets adjusted accordingly. You can also do things with these contracts. You can write whatever arbitrary code you want. So you can have complicated rules, like maybe several people's approval is required to do something. It's when you create one of these contracts, you literally define what it does. The way you create it is you just send a transaction with no recipient. And then the data that you put in that transaction becomes code in the virtual machine. So this becomes a program, and it'll just run whatever you want. Basically in public, totally transparently, and it'll just sit there waiting for you to do stuff with it. What are people doing with it? They're doing all sorts of cool things that require a public computer that's transparent and kind of lives in a shared space. It's people crowdfunding, working on governance, prediction markets, accounting, art ownership, exchanges, gambling, of course, yeah. There's scams, scams a dime a dozen. In this space this early, get familiar with those and avoid them. But then there's also really cool, generous things. Yeah, peer-to-peer lending. There's as this ecosystem matures, it's got a lot of cool potential, and a lot of people are pretty excited about it. And that's my intro for this. Thank you.